Good day, students. Welcome to math.surf.com. On this clip, we're going to be going over problem 2 of the 2004 AP Calculus AB free response question, focusing on area, volume, and solids with known cross-sectional areas. All right, let's take a look at problem 2. It reads, let f and g be functions given by f of x equals 2x times 1 minus x and g of x equals 3 times x minus 1 root x for 0 less than or equal to x less than or equal to 1. The graphs of f of g are shown in the figure below. Part A, find the area of the shaded region enclosed by the graphs of f and g. Okay, so we're trying to find the area of this region right here. So let's go over the formulas that will guide our setup process, and then we'll apply it to this scenario. Okay, so formulas. Now the orientation of your functions and also that of your slice basically tells you how to set up your formula. Okay, so let's say you have a function that is oriented vertically. Okay, so you have a function on top and a function on the bottom, something just like this. Okay, now because you have a top-down orientation of your functions, your slices are going to be oriented in the vertical orientation. So you're going to have a top-down slice. Okay, so in this case, you're going to be accumulating infinitely narrow rectangles from the left to the right. So let's say you're starting from this point right here, projected to your x-axis, you have a x left, and then all the way to the right, this is x of the right. Okay, in that case, your area is going to be the integral. So it's going to be the integral from x left to x right. Okay, rectangle is going to be sweeping from left to right of the function on the top, f top, as a function of x, minus the function on the bottom, f bottom, as a function of x. Okay, and your dummy variable here is going to be dx. Now, one thing you'll notice is that if you orient your rectangle vertically, all your variables are going to be in terms of x. So notice your limits of integration, your functions are in terms of x, and your dummy variables in terms of x. Okay. Now, what if we have our function oriented horizontally? Let me just do a real quick label in here. This is f top, and this is f bottom. Okay, so we can clearly see that this formula is applicable to this scenario right here. But what if we have a left-right orientation of our functions? So let's say we have a function like this. Oh snap, that's not a function. This looks something like that. And another function that looks something like that. Okay, so you can see that this function is oriented left, right, right? You have a function to the right and a function to the left. In this kind of configuration, you are going to orient your slice horizontally. Okay, you're going to have a horizontal orientation of your slices. So what we're going to do is cut up this area into infinitely narrow rectangles that are oriented horizontally. Okay, so in this case, instead of going x left to x right, we're going to be going from the bottom. We're going to be going from, let me use something straight here. We're going to be using y bottom to y top. That will be our limits of integration. Okay, so we're going to have y bottom to y top. All right, let me split the area right here so we don't get things confused. Okay, so in this case, our area is going to be given by the following integral expression. It's going to be the integral of y bottom to y top, because our slices are going to be configured or oriented horizontally and they're moving from the bottom to the top, of Instead of having the function on the top minus the function on the bottom, guess what? We're going to be having the function of y on the right, function of y on the right minus the function of y on the left, okay? And our dummy variable, of course, is going to be dy. Okay, so this is basically the formulas for finding the area of a region bounded by two curves. Okay, so there you have it. And let's label our functions. This is f on the right is a function of y, and f on the left. So one thing you want to keep in mind is that the orientation of your slices tells you what variables to use. So whatever direction your slice is perpendicular or pointing to, you're going to be orienting your function. Your function is going to be in terms of that axis, okay? So if you see this function right here is pointing to the y-axis, the vertical axis, so everything is going to be in terms of y. And if you look at the slice right here, it's pointing to the x-axis, so everything is going to be in terms of x. All right, so we know the formula that we're using. So for this problem, we're just going to set it up and plug it into our calculators, okay? So the area, so in this function, let's label it. This is going to be f top right here. This is f top. And this g of x is going to be f bottom. Our rectangle is going to be oriented vertically because we have a top-down orientation, okay? So everything is going to be in terms of the x-axis. So our area is going to be, using this setup right here, the integral of the intersection point of x to the left, which is 0, all the way to the intersection point of x on the right, which is 1, of the function on the top is f of x. So of f of x minus the function on the bottom is g of x. Okay, dummy variable is dx. That's the width of this rectangle right here. This narrow rectangle has an infinitely narrow width, which is dx. So this, evaluating this integral will give us the area between these two curves, okay? Okay, so we're going to be using our TI-89 to do this problem. Now, you might have stored a function in your calculator before, so we have to make sure that we don't have any functions stored in the calculator. So press second function F6, and you can clear variables A to Z. Okay, under the first menu on the F6, first option, press enter. So it'll say clear one character variables A to Z, and the current folder, press enter again. And then you can just type in f of x just to test to make sure that you don't have anything stored there. And then g of x, because you might have stored something there in your practice and then you have that distort your answers. You don't want that. Okay, so I have nothing stored. So what I'm going to do is store the first function in f of x. So we're going to have 2x times 1 minus x. This is a calculator active section, so we don't want to waste time trying to do stuff by hand. Just want to store everything in a calculator. So 2x times the quantity 1 minus x, you store that in f of x. Enter. Okay, we get an error message here. It says invalid implied multiply. So press escape. Now, we have 2x in the parentheses here. The calculator has some issues with that. We want to explicitly state that we're multiplying 2x by this quantity. That should work, hopefully. Okay, good. So when you have that implied multiply, you have to put a multiplication symbol explicitly where you're multiplying a variable by a quantity, okay? Now for g of x, we have 3 times the quantity x minus 1 times the square root of x, and that will be stored in g of x. Okay, so we just store it once and that's it for the entire problem. Enter. Okay, this worked nicely. So we have g of x and f of x stored. Now let's go ahead and enter this expression here. So we're now going to be computing the integral of f of x. So f of x minus g of x, comma, variable of integration is x, lower limit is 0, upper limit is 1. Like that. All right, press enter. Okay, it gives you the decimal result. Let's find a numerical approximation, pound enter. And then 1.133 repeating. So let's take it to 4 decimal places. If you put 17/5, that's correct too, okay? But for calculator active questions, in most cases, they want the decimal approximation. So in this case, we have 1.1333 as our final answer. That's the area. Okay, now how is this problem graded? Well, you get a total of 2 points here. Okay, you have, let's see, for the integral setup, this entire integral right here, you get 1 point, and then you get another point for getting the correct result. Total of 2 points. Okay, remember, don't just enter stuff in your calculator and write down the final answer, assuming that the grader knows that you entered the correct expression. You might not even get any credit. You have to show your calculus. Whatever your integral expression you're entering in your calculator, you have to write it down. Okay, and then put the final answer so you can earn your complete credit. All right, let's take a look at the B part. It says, find the volume of the solid generated when the shaded region enclosed by the graphs of F and G is revolved about the horizontal line y equals 2. Okay, so if you look at the orientation or the position of these two functions, they are both beneath 1, so 2 is going to be somewhere up here. So you have a situation where the bounded region is beneath the axis of rotation. Okay, that's important in the setup of our formula. So let's take a look at the formula for this scenario first, and then we'll apply it to this problem. So formula, what we're going to be using to find the volume of the resultant solid is the washer method. Okay, so let's say you have a bounded region configured in this orientation, up and down. You have a bounded region, and then you have an axis of rotation that's above the bounded region. Okay, so your area, the area of the volume of the resultant solid when this region is rotated about this axis that's above the region is going to be, so the volume, let's change the color here. So the volume is pi. Now let's do the integral first. So volume is going to be the integral. Now, since we have a slice, we're going to be slicing up down, as like we discussed earlier, where a slice is going from up to down. Our x-axis is going to be going from, we're going to be going from x left to x right. Okay, so it's going to be from x left to x right. Okay, times the integral of pi times the outer radius square, so big R, I'm going to call it R outer, square, minus pi times the inner radius square. Okay, and this entire thing dx, because our slice is oriented in the vertical orientation, okay? So it's going to be dx. So this is basically the formula right here. Now, what is the outer radius and what is the inner radius? The outer radius is the distance from the further function to the axis of rotation. Okay, so let's call this. Let's go ahead and determine what both of them are. Okay, so for this configuration, this function right here, the one on the bottom, I'm going to call it f bottom. The distance from this function to the axis of rotation will be the outer radius. Okay, so the distance from here all the way to here, that's going to be the outer radius. Let's go ahead and mark it. So this is going to be big R, outer. And then the distance from that top function from here to here, this distance will be your inner radius. Okay, so this is going to be R inner. All right, so when you subtract these two, you get the radius of your washer. Okay, and then you're going to rotate that region around. I'll show you an animation in a second. So this formula can be written as follows. Now, let's call this is F bottom, and this right here is F top. Our axis of rotation is the line y equals a, so let's just call it a. F of x equals a. Now we want to simplify this formula, make it a little bit more precise. So we have the integral from x left to x right. Now since these two terms have pi's next to them, we can factor out the pi. Now the outer radius is simply going to be a, which because it's higher, minus the function on the bottom. Okay, so we're going all the way from here to here. That's your outer radius. So a minus f bottom as a function of x, close that, squared. Okay, pi times this will give you the area of the bigger disk, pi r squared, area of a circle. Okay, and then minus, we're going to have a minus the top function because that's the one that's in closer to the axis of rotation, which makes it the inner radius when subtracted from a. So f top of x square. Dummy variable is dx. All right, so this is basically how we're going to set up this particular area. All right, it looks this way because a is above the functions. Now guess what? If it were the case where the axis of rotation, a were beneath the functions, what will have happen is that these two will switch, and the order will switch. You have f top minus a squared minus f bottom minus a squared. Okay, you switch the terms in the parentheses, and then you switch the order of the radius. Okay, because you have a different configuration where the top function is actually the what determines the outer radius, and the bottom function determines the inner radius. But this is what we're going to use for this example. Okay, all right. So let's go ahead and label it and then apply it. So our axis of rotation is a equals 2. Okay, that's what was indicated earlier. A is 2, and then this right here, this is our f bottom, g of x, and this is our f top. All right, of course, this is our x right, and this is our x left. And then the orientation of our rectangle, we know it's top down, and then we're going to be rotating around that axis. Okay, so let's set up our equation for the volume. So the volume is going to be pi times the integral from x left is 0, x right is 1. And then we're going to have the axis of rotation, which is 2, minus the function on the bottom, g of x, square, minus the axis of rotation again, 2 minus the function on the top, f top, which is f of x, square, and our dummy variable dx. Okay? Now let's go ahead and substitute what the functions are in here. So we're going to have pi times the integral from 0 to 1 of 2 minus g of x. g of x is 3 times x minus 1 root x. Okay, so you square that. Pi times this radius squared gives you the area of the outer disk minus 2 minus f of x is 2x times the quantity 1 minus x. Close that. Square dx. This gives you the pi times this gives you the area of the inner disk. When you subtract it, you have the washer. Okay. All right. Now let's input this into our calculators. We're going to use the upper expression because we already have stuff saved in there, so that really makes our life easy. All right, now entering this is very tricky. It's very easy to make mistakes. So I'll show you some neat little tricks you can use to aid your entry. Okay, so we're going to have pi times the integral. Okay, so I have the integral. I'm going to put in 1 parenthesis square minus another parenthesis square. Variable of integration is x, and you are going from 0 to 1. All right, what just happened here? Well, what I'm doing is because we have this long thing to enter into, we're entering stuff in here. I'm putting the parentheses there first, and then I'm gonna put f of x here, put f of x here, and then I'm going to put g of x here. Okay, so I just put the parentheses there as placeholders so I don't get myself confused, because there's a lot of parentheses going on. Okay, so in here, I'm going to put in f of x. So alpha f parentheses of x, and then go into the second parenthesis right there. You see that? And then you put in what? What we're going to put in? G of x. Okay? Sometimes I lose track of my parentheses, so that's why I like to create the space first, and then you insert the functions afterwards. And please do not forget your pi. You got to put that in there first before you evaluate your antiderivative. Okay, so let's take a look at what we just entered. We have f of x and then g of x. You take a look at what we have right here. You can, if you notice, there's a mistake. Well, actually, there are two mistakes that have been made so far. Can you see what the two mistakes are? First of all, f and g are not the order of the functions here. You have g first and then f. And then you also have to put the 2 minus piece, okay? So let's switch this around, make this f. And then let's change that to g. Oh, snap. Make that g. Okay, so we have the functions in there. Now we're going to put the 2 minus, okay? So right next to the g, just put 2 minus. And then next to the f, you put 2 minus. Okay, so you notice how it's set up. And then now another thing, let me put in the answer first. So diamond enter. After you enter your expression into the calculator, hopefully you do not get any syntax errors. One good practice to do is always go back to what you entered and see if it matches what you want to enter, okay? So pi 0, 1, 2 minus g of x, pi 0, 1, 2 minus g of x squared, good. Let's go to the right, 2 minus f of x squared, 2 minus f of x squared, that's exactly what we want. So had it been if you'd reversed your results here, your functions, you'll end up with the opposite. You end up with a negative answer, which is not correct, okay? Because you're looking for a volume. Now, there goes your final answer. So let's go ahead and write it, 16.1792. So the answer is 16.1792. That's your volume. Okay, now let's see how this is graded. For this one, you get 1 point for putting this constant here, this pi, and then having your limits of integration. You get 1 point. And then your integrand earns you 2 points. Final answer, 1 point. Total of 3 points for this question. All right, so let me give you a little visualization of the solid that we just computed the volume of. So this is the region right here bounded by these two curves. So what we're doing is rotating it about y equals 2. and then computing the volume of the resulting solid. Okay, let me use a different one. So there goes the region stretched out, and then you just basically rotate it about the line y equals 2, and that region, that's the solid that we're calculating the volume of. And then you see a nice little washer right there? That's what we're accumulating from left to right to generate the volume of the resultant solid. So if you want a 3D visualization of what we were computing the volume of, there you go. All right, let's take a look at the C part. It says, let h be the function given by h of x equals kx times the quantity 1 minus x. For 0 less than or equal to x less than or equal to 1. For each k greater than 0, the region, which is not shown, okay, you gotta be careful, h is not shown. What was provided was f and g. This is not shown, all right? But it's still a quadratic function anyway. Not shown, enclosed by the graphs of h and g is the base of a solid with square cross sections perpendicular to the x-axis. There's a value k for which the volume of the solid is equal to 15. Right, but do not solve an equation involving an integral expression that can be used to find the value of k. So in this one, we are not solving, we're just setting up the problem. Okay, so let's start by taking a look at the formula for solids of known cross sections. Okay, we're doing cross sections here because you have a cross section, that's a giveaway. So the formula is the volume equals the integral. Now it's perpendicular to the x-axis, so guess what? Everything is going to be in terms of the x-axis. So we're going to go x left to x right of the area of a cross-sectional region dx. End of story. There's no pi's here, no squares, no revolutions, nothing. Okay, so the hard part about this problem is trying to get a good sketch down, and then you can excel from there. So what I'm going to do, I'm just going to tilt my y-axis a little bit and try and sketch the region in a way that gives you a good um, understanding of what's going on. So there goes the function, this one right here, h of x is on top. Okay, so let's draw that. H of x is something like that, and where is the other one? G of x is on the bottom, so something like that. Okay, how do we know? If you take a look at this function right here, this is a quadratic function with zeros at 0 and 1, and k is greater than 0, which means that your parabola is going to be facing down, because when you distribute this kx to this negative x, you have a negative x squared, and that's going to be a downward opening parabola. Okay, just like f, it's just that it's slightly different. Okay, so now this is a region. Okay, now the region between these two functions is the base of a square. Okay, so what are we going to do? Just draw in the square. So this right here, that's the base of your square, and then you draw your square, something like this. It doesn't have to be perfect. So there goes your square. Okay, now what we're going to do is extract the area of this square and insert it into this formula right here. So what is the area of the square as a function of x? If this side length right here is s, the area of a square we all know is simply side square. Okay, so all we need to do is find the length of the base, and that will help us find out what the area of the square is. Okay, so let's go ahead and do that. So area is s squared, but s is the length of this base right here, which is the top function minus the bottom function. So s is simply going to be the top function. Do you remember what that is? That's the h of x function, right? And then the bottom function is the g of x function. So s is the difference between these two functions. So it's basically h of x minus g of x. So now, how is this useful? What are we going to use the side for? Well, we want to find the area as a function of x. So instead of s squared, I'm going to take this s out and I'm going to put in h of x minus g of x square. That will give me the area of this square right here. Okay, so what we're going to do is we're going to accumulate all the squares from this point to this point with the base length of h of x minus g of x, and that will give me the volume of the resulting solid. Okay, so let's go ahead and do it. So we're going to do volume is equal to the integral x left is 0, you're starting from here, and then x right is 1. Okay, and then there 0 to 1 of the area. The area is s squared, which is h of x minus g of x quantity square dx. Okay, you notice all these are x values because our cross section is perpendicular to the x-axis. Okay, if it were perpendicular to the y, everything will be in terms of y. So let's substitute the functions in. So we have the integral from 0 to 1 of h of x. H of x is kx times 1 minus x minus g of x is 3 times the quantity x minus 1 root x. And this entire thing is squared dx. Now we're told that the volume is equal to 15. So guess what? This is going to be equal to 15. So setting 15 equal to this expression, this is the equation that we have to solve to determine the k value that will satisfy a condition where the volume was going to be equal to 15. Okay, so there goes your final answer for question number 2C. Okay, so how is this one graded? So for this one, the integrand, h of x minus g of x, that one, the integrand will earn you, I'm sorry, including the square, we have to, the integrand is everything between the integral symbol and the dummy variables. So this entire expression right here earns you 1 point, actually earns you 2 points. So you get 2 points for that. And then setting it equal to the answer will earn you another 1 point, for a total of 3 points for question number 2C. Okay, so what does this solid look like? Let me show you a visualization. So this is what the solid is going to look like, the solid that we're talking about. So like I did earlier, I rotated the region about the y-axis slightly so I can basically draw that square. So you see that square happening right there. And then when you accumulate all the squares together, you have a solid that looks just like that. So that's basically what the solid looks like. Okay. Okay, so if you want to take a look at the visualization as to what the resultant solid looks like, so let's take a look at it. If you notice, the shape is rotated about the y-axis, so just to give you a visual as to how the height of the square looks like, okay? So when you tilt it, it's easy for you to draw a cross-sectional shape. Sometimes it could be a triangle, a semicircle, in this case is a square, but when you rotate, it's easier for you to put that sketch in and capture the portion of the cross-section that's related to the two functions. In this case, it is the base of a square, okay? So let's see what it looks like when we accumulate all the squares together. Let's see what the resultant solid looks like. So rotate, we're going to be drawing the squares that go like that, and then the resultant solid looks something like that. Okay? Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your preparation for the AP exam, do give us a thumbs up. Your positive feedback is very helpful to us. If you have any questions or comments, just place it in the comment section below, and we'll be more than glad to support you. More clips can be found on math.serve.com, and of course, do not forget to subscribe so you can get updates to other cool calculus tutorials such as this. Thanks again for watching, and have a wonderful day. Goodbye.